Welcome to our 4 o'clock press conference, See Through Seas, Imaging the Planet's Hidden Interior. We have 3 speakers, and they'll be speaking in this order. Gus Nolet is Professor of Geophysics at GeoAzur, the University of Nice, Sophia Antipolis in France, and he's the George G. McGee Professor of Geoscience and Geological Engineering Emeritus at Princeton University. Second speaker will be Jan Hello, Director of R&D at the Institut de Recherche pour le Développement and GeoAzur France. And then we'll have Frederick Simons, who's Associate Professor with the Department of Geosciences at Princeton.
Thank you. So what we are going to tell you is that in an experiment that started 10 months ago, we have proven that it is technologically possible to measure strong earthquakes by robots that float at a depth of about between 1,000 and 2,000 meters. And why is this important? Well, seismic waves are not only hazardous, they also give us a lot of information about the interior of the Earth. And especially when they go through a region that's a little hotter than normal, like, for example, the Hawaii plume. A seismic station on land, will see that it comes in a little late. And this, if we have a few thousand of these small delays, we can use computer-aided tomography, just like a CAT scan in the hospital, to actually make an image of these temperature variations in the Earth. The big scientific question behind that is that we still don't understand how the Earth has been able to keep roughly the same temperature for billions of years, and not too cold, not too hot, just fine to make the development of life possible. Now, not only are we doing this for these purely scientific reasons, here is something that happened 2 weeks ago. We took one of these robots, put it near the triple junction in the Indian Ocean in the water, told it to go down and come up after 24 hours to tell us the state of health. After 24 hours, it came up with this very small seismogram that you see in the upper left corner. This was recorded nowhere else on Earth. While it was at the surface and transmitting us the data that we needed, a magnitude 5 earthquake happened that was recorded on land, and that was the start of a seismic swarm. When the mermaid, as we call them, went down, it got 200 triggers in the space of 24 hours. And when it came up again, it sent us the best seismograms, and you're looking at these seismograms here. None of these little earthquakes has been observed on land. So our instruments can both record seismicity in the oceanic domain, and they can provide us the necessary information to understand the Earth as a thermal machine. You can compare our situation a little bit to a CAT scan in the hospital, where 2/3 of the sensors are broken down because we have hardly any seismic stations in the oceanic domain. The history of this project starts actually 10 years ago, when Frederick and I put a hydrophone, which is a microphone for acoustic waves in the water. We put a hydrophone on an oceanographic float. These floats go down, measure the currents in the ocean, but they are not designed to do what we are doing with it. We floated it for a few days off the coast of San Diego, and by sheer luck, we saw that we could actually see an earthquake rise above the noise. It was a magnitude 6 at a distance of some 5,000 kilometers. This gave us the idea that, yes, it should be possible to open up the oceans to do seismology. But it was met with a lot of skepticism, and it was difficult to get funding. 5 years ago, I moved to France to work with Jan here, who is an excellent engineer in a laboratory that works with ocean bottom seismometers. And the other thing in Europe is the European Research Council, or the ERC, is really committed to fund what project that they call high risk, high reward. With that funding, we actually were able to build a small fleet. And just before Christmas last year, we put 2 of these instruments in the Mediterranean. And this is a trajectory that they took over 10 months' time. The design is such that we target magnitude 6.5 earthquakes. We are happy if we can see a magnitude 6.5 earthquake above the noise. Since we launched them, the Earth has seen 39 of these magnitude 6.5 earthquakes, of which 18 are at a distance range between 0 and 10,000 kilometers. If they are further away, the earthquake waves actually cross the core of the Earth and they are more difficult to see. Mermaid 17 and 18, one of them recorded 10 of these events, the other one 11 out of the 18 events. But they also, each of them recorded 5 events, or 5 waves that actually had crossed the core of the Earth. And to our great surprise, if the weather conditions are cooperating, we can actually see magnitudes as low as 5.5 from as far away as Mexico. So this is an unexpectedly good performance that really gives us confidence that we can open up the oceans for seismology. To test that, we also put instruments in the Indian Ocean, which is notoriously very, very noisy. So I'll show you first a seismogram from the Mediterranean. It's a magnitude 6.7. If we go to the Indian Ocean, this is a magnitude 6.5. You can see that it's more difficult to see. Yet we are able to see the target magnitude of 6.5. We are able to see it in the Indian Ocean as well. So with this success, we hope that in the very near future, we shall be able to deploy at least a few hundred of these. There's one more technical hurdle that we need to take for that, and that is that since we are using the machines that have been designed for oceanographers to put our hardware and our software on it, these last probably only 2 years. We still have to find out how long they actually will live on their battery power. But it's only a matter of a slight technical improvement to make these larger. And both Jan and Frederick have their own ideas about how to expand the size of the instrument so that we have a better and a longer battery capacity. With that, I give to Jan to give some more technical details about the instruments.
Technical development was, of course, helped by the fact that we used the floats that had already been developed for oceanographer to measure temperature and ocean currents. But these floats are simple compared to the Mermaid, which is essentially a floating computer that never stops to listen and analyze the sounds that it's picking up, and that can communicate large data packets to a satellite. We needed to have about twice as much electronics in there to make them in floating seismometers. Okay?
You need to speak more in the microphone.
Okay. From the very beginning, we teamed up with Teledyne Web Research in Massachusetts to construct the Apex floats. For the electronic development, we were assisted by Océan, a small engineering firm in France. Océan is spelled with an S, not with a C. One major challenge was to minimize the power consumption despite the continuous computing that it does. We launched the Mermaids with the equivalent of 40 D-size batteries that you may use in a flashlight. Once these are exhausted, the float drifts helplessly unless we let it sink to the bottom or pick it up. The processor that does the computing is mounted on a separate card, which we call the Mermaid card. This card has to communicate with the control card of the float so that it can command the float to come to the surface once it has picked up a reliable seismogram. If it is in doubt, it will store the seismogram in its memory and transmit it later when it comes to the surface with more promising data. It takes the Mermaid about 5 hours to come to the surface. But in that time, it drifts only a few hundred meters, and we can live with the error in position as much or as large as 1 or 2 kilometers. The first thing that it does is to pick up a GPS signal to find out where it is. South in the Indian Ocean, we had to solve some unexpected problems and make sure that the antenna sticks above the water, the waves in fact, in order to get a fast GPS position, mainly because the waves are higher in there than in the Mediterranean. Satellite transmission is our second largest consumer of battery power. So we also worked at data compressions and fine-tuning the algorithm so as to minimize the number of false triggers. Signal look like an earthquake, but are from some other sources. With the help of Dana Swift from the University of Washington, we developed a satellite communication system for Iridium to transmit the large volume of data we recorded. We also developed a single antenna that can handle both GPS and iridium communication. From a logistic point of view, we can conclude that the mermaids are easy to launch, much easier than an ocean bottom seismometer. Also, we don't have to recover them, and they deliver the data in almost real time, and allow us to adjust parameters of the algorithm that identify earthquakes waves among the many other noises that you can hear underwater in the ocean. The deployment of mermaid is therefore far less costly. With the success of our mission so far, we are already looking forward to our next launch of 10 mermaids to study the mantle plumes under the Galapagos Islands. For a worldwide network of few hundred mermaids, we shall wish to prolong their expected lifetime to 5 years and extend the instrumentations to include the much higher acoustic frequency used by meteorologists and biologists. When designing the mermaids, we took special care to minimize power consumption. But even if all the components are ultra-low power consumption, the existing mermaids cannot operate for more than about 2 years. The precise lifetime is not known, since we have only been operating them for a year now. And it depends on how often it comes to the surface to transmit strong earthquakes. In the near future, we shall wish to extend the lifetime to at least 5 years. For that, the existing oceanographic floats that we are using now are not big enough. To increase the battery capacity, we are developing a new generation of floats that use the same 17 inches glass spheres that we use for ocean bottom seismometers. These are capable to resist pressure down to much greater depth and can hold more than 2.5 times the battery power of the current mermaids. Others are working on similar vehicles. However, the one we developed is designed around the acoustic monitor we present at this AGU meeting, and will also accommodate acoustic sensors that may serve biologists who are interested in monitoring in the whale populations, and meteorologists who may be able to measure rainfall at sea. But let me hand over to Frederick Simons now.
Okay. Signals and noises have been mentioned, and the signals are going to be, for us seismologists, are going to be earthquakes. And before I say any more, I should want to point to you the 3 figures here. The one on the left is a mantle earthquake. So the star is an earthquake, and the triangle is a station. And so, in other words, just an earthquake sending a ray or as a source of energy through the Earth's mantle and recorded on the seismometer gives us information about the interior of the Earth. This diagram is to scale, where the thick black outer line is the Earth's crust. This really is not what we're talking about. Crustal earthquakes are not, or the crustal structure is not what we're particularly after here. But we're looking for earthquakes that, like in the second diagram, also perhaps, as Guus was showing an example, propagate all the way through the Earth's core. So the shaded area here are to scale the light shaded area is the Earth's outer core, and the dark shaded area is the Earth's inner core. The light shaded area is liquid, and the dark shaded area is solid iron. That's what is at the interior of our planet. And then the various little earthquakes, the close by earthquakes, well, they just send energy and are recorded over very short distances and don't do a very good job to image the interior of the Earth as a whole. Now, these are the various classes of earthquakes that have all been recorded on these mermaids. And let me now tell you something a bit about the noise that we also observe in the ocean, which is really a main concern, not only to identify it, but also through the signals which we need to record in a high signal-to-noise. And then all of that requiring power, which we need to minimize on our instruments. So the top panel here shows that earthquake, that very first one that we ever recorded on a mermaid, which is a magnitude 6 earthquake at about 5,000 kilometers. All the left column shows the data as recorded by the mermaid. So this is literally just acoustic pressure variations at depth of, at the so-called cruising depth, several hundreds to a kilometer down the ocean surface. And so it's a whole bunch of noise that gets larger, and that's where our P wave arrival is, the first arrival, the compressional wave, which is marked by P. In the middle column, we see the evolution of energy as a function of frequency or wavelength, and also as a function of time. And so the panel is between 0 and 2 hertz, and the red thing there in the first diagram on the top there in the middle that red band where we expect our faint and distant earthquakes to come in and be recordable, that is also in general a very noisy band. But nevertheless, that intensification of the red colors there shows you that there was increased power. But compare that energy with the panel right below, or the panel even right below. Those are those closed by earthquakes. Their waves haven't traveled much through much of the Earth, and so all of these highest frequencies shown in red are still present. So we really are, with our mermaids, looking through some very faint signals. So what makes it all work in the end is that the computation in the middle is not something that we care to do on board of the mermaid, because it involves lots and lots of operation. Rather, we compute something that is shown in the column on the right, which is called the wavelet transform. And wavelets are time-frequency building blocks of signals which are happening, chances are, inside of your digital camera. If you take a picture with your camera at a certain megapixels and there's RGB channels and it's a certain digitization, your pictures all come out in different sizes. And that's because they're put through compression algorithms that store only the amount that is really important. And it's the same here. Every one of these events we reduce to a sort of a digital fingerprint, where instead of pixels in your camera and how they compress in space and frequency, they become little bits of energy at a certain scale on the vertical axis and as a function of time. And so every one of those is for us a little barcode that in the latest implementation of the algorithm, which was developed by Alexei Sukovich, who is now at the University of Brest in France, we're studying noise upon noise upon noise to learn, as a learning algorithm, what the telltale signatures are of these various events, seismic and non-seismic, in this wavelet scalegram. So here in the next panels here, the top panel is a ship passing by. It gets louder. In the middle column there, you see these telltale stripes of energy because the rotors, the propellers of the ship have very distinct harmonic frequencies. The second line would be an airgun campaign. This is an exploration company shooting with an implosive device and bringing energy into the subsurface. This is how oil exploration gets done. And so this is a series of very loud bangs that are nevertheless doesn't fool our recorder. And then the lowermost one is a record of an earthquake that has trapped all of its energy pretty much in the sound fixing and ranging channel, which is that channel that waves like to swim into and submarines like to stay out of, because it transmits sound over very, very long distances. So in the next slide, I'll just show you some other ones of these signals, and these are all various whales. So this is another application for mermaid and its ilk, which is to identify by their spectral wavelet or even just in the acoustic record the various species of whales, where they are, at what time, and what their sort of population makeup is. So the various, the three ones are a fin, a minke, and a blue whale, and you can tell them apart from how they modulate the frequencies and vocalize basically with very telltale signatures. So I always like to make the observation that compared to that airgun campaign of the Shell oil shooting offshore somewhere, that it scares the whales because it's very loud, but it certainly doesn't confuse them because the patterns they emit are very just like the seismic events, have a very distinct signature. Now, and then the last bit is about how we can make another alternative to mermaid. This is something that we have been working on at Princeton, continuing, I should say, at Princeton, and also now involving Bud Vinson at the University of Rhode Island. And we call our extension of mermaid the sonomermaid, because it is a combination sonobuoy and a mermaid. And so this instrument has a top part that is always above the wave basis. And so that's in the upper left there. There you see the series of antennas that does pretty much the same data transmission. And then using a variety of suspension techniques, we suspend a whole array of hydrophones, which once again record that acoustic pressure at the same or various depths in the ocean. And the key thing that mermaid didn't have, that the sonomermaid has, is Well, because we are also in the wave bases, we are able to harvest the motion of the waves and get extra energy out. So this is called a wave heave generator that we can build in, where it's going up and down anyway, might as well extract some of the energy. And instead of making multiple dive and surface cycles, we suspend our instrumentation from a cable. And then once I've said that, that means that any other type of instrumentation, whether it is acoustic for meteorological or biological or seismological applications, it can be equipped with various other sensors, such as for biogeochemistry to measure fluorometry or pH in the ocean, or any other thing that can be dangled and off a cable and powered from above can be seen as a vehicle. So this is going to be with the multi-mermaids to probably lead to an entire family of mermaid-like devices, but the main application, once again, for us is terrestrial seismology.
Okay.
Thank you. Do we have any questions from the floor?
Hi, I'm Tia Ghosh from Live Science. I guess a couple things. I'm not clear on how this is different from some of the hydrophone networks that are all throughout the ocean and that people have been using for decades. And I guess the other question is, maybe I missed it, but it's not clear to me why you can detect these earthquakes that go through almost all the interior of the core this way as opposed to on land or with existing seismographs.
The answer to the first question is there are hydrophone networks, there are military networks, but there are also tethered hydrophones. They do not move. The important thing for us is that the mermaid changes its place. So if there is a big earthquake at some point, we get one piece of information about the Earth. The time that there is an aftershock, maybe 2 weeks later, the mermaid is somewhere else. It is as if we have another seismic station. And this is the same principle that's being followed by the seismologists in the US with the array that's called US Array, which has moved in the past 10 years from California to the East Coast. Rather than having a fixed network, they move the network so that every year there is a new piece of information, even if the earthquake is at the same space, at the same place. And I did not get your second question. Can you repeat it, please?
Oh, yeah, I just didn't understand why this will allow us to actually detect those earthquakes that are traveling almost through the entire core of the Earth, where our existing seismographs don't, and whatever.
Well, existing seismographs see them much easier than we do. The point is that 2/3 of the Earth is ocean. And we have only a few seismic stations on ocean islands, but for the rest, we have no data from the oceans.
So it's quite literally like in the diagrams, if there is no ray path connecting the source to the receiver, you haven't been there. And so that puts a premium on putting new instrumentation out in that 2/3 of the area that hasn't been instrumented. And then as to the tether, I should add that it's very expensive to put anything on the sea floor. This can be deployed by people throwing it off overboard. It doesn't even have to be a research ship.
Just to emphasize, if you do a CAT scan in the hospital, the sensors rotate 360 degrees. Imagine that it rotates only this far, and that the rest you don't have any information. You wouldn't get a very nice image in the hospital CAT scan.
Do we have more questions? Questions are reserved for working press.
I'm a freelance. Okay. I'm a freelance writer. Janet Chappell is my name. I just didn't catch how your research is funded. Would you explain that, please?
Europe has the European Research Council. Maybe Siert Kloeting is here, who is in the Scientific Council of the ERC. Maybe, Siert, you can say something about the ERC?
Yeah. For those of you who have to hear earlier today for the town hall meeting on ESC, we communicated to the community some features of ESC. It's a young instrument. It's part of the portfolio of instruments of the European Commission to fund research in Europe. The only criterion for the European Research Council is scientific excellence. It's wide open to applications, bottom up, so it's all PI-centric, and these are quite substantial grants. In the case of an advanced grant, and Guust is a recipient of an advanced grant, we talk about €3.5 million. You have to multiply this by 1.4 to get it in dollars, and there's a bonus of another €500,000 to bring people from outside Europe in the European research area. The flexibility is very large, and the prime idea is to fund, what Guust has also mentioned, high risk, high reward research. And what the European Research Council has done more recently is also develop an add-on instrument, the proof of concept, which enables to further develop the idea in the direction of innovation. And Guust Nolet is also a recipient of such a proof of concept scheme, and that enabled him to make the connection to this company, Ocean, which is very vital for the further development of the instruments. We have a Destination Europe event, Thursday and Friday, with full information on all the research instruments available today in Europe. And this is quite a different portfolio that was there before. And to give you an idea about the budget of the European Research Council for the next framework program of 7 years in Europe, that is a budget of €12 billion. And that is nearly a duplication of the budget that was there for the previous period. That was a budget of 7 billion. And that is, of course, a remarkable development for a continent where some of the countries face economic problems. But nevertheless, there's a major investment in science.
Do we have any more questions?
Christina Reed, Discovery News. Just a quick question. How often are they resurfacing? They go down 1,000, 2,000 meters and then come back up within many hours?
Yes, we have a whole protocol. If nothing happens, then it will come up every 10 days, so at least we know where they are. But they have, whenever they record something that they think is an earthquake, it assigns a probability. If that probability is higher than about 90%, we tell it to come up to the surface and give us the data. If it's lower, but it might still be a good earthquake, it will store it into memory and it will send us whenever it comes up next.
Hi, I'm Bas den Hond, freelance for Trouw in the Netherlands. Goedemiddag.
Goedemiddag.
Good afternoon. I have two questions. The first one is, could you address the depth at which the mermaids work? Is that some kind of a compromise between cost and proximity to the sea floor, or is 1 to 2 kilometers actually where you want to be?
It's a very good question. There is in the oceans there is something called the sound channel, and you don't really want to be in the sound channel. The problem is that, for example, in the Indian Ocean, it's almost impossible to escape the sound channel. You would have to go almost to the bottom. But in the Mediterranean, we can escape the sound channel, and that it's a little bit by trial and error. We can, every time that it comes up to the surface, we can change the depth where it goes. And we have been cruising at depth as deep as 2 kilometers and as shallow as 700 meters.
Okay, so you don't want to be too deep because that's where the sound channel is.
No, the sound channel is actually nearer the surface. But in the Indian Ocean, it extends to almost the whole ocean.
But as long as you go under it, there's no need to be closer.
We hope.
Ever closer to the bottom.
We hope, because so far we have not been able to really go under it in the Indian Ocean.
Okay. My other question is, in this picture, the P wave comes comes up to the detector nicely vertically. I guess in practice it comes from all over the bottom. How do you get a nice signal?
The P waves come from deep, if they are from faraway earthquakes. It is possible that the sound reaches us actually through the water if the earthquake is very, very nearby. But normally, the P wave hits the ocean bottom, and then its propagation path in the water is practically vertical.
Hi, Tim Olson from Earth Magazine. I just wanted to double check about the timeline. You said you've used two mermaids so far, and I think you said you had plans to use 10 more, and I guess I just wanted to know when you were going to deploy those first, and then I guess, what the ideal scenario is. I assume you'd love to deploy even more than that.
Yes. So the timeline was, we put 2 in the Mediterranean at just before Christmas. We put 2 in the Indian Ocean in March, but we had to learn a lot about the noise characteristics in the Indian Ocean before they actually were programmed such that they perform as we want them to perform. And once we discovered that, we just 3 weeks ago or 2 weeks ago, we put 2 more in the Indian Ocean. We are geared up to put 10 around the Galapagos Islands because we are very much interested in the mantle plume that is likely to exist under the Galapagos Islands. And that will happen in March. Then that's our whole fleet as we have so far. The idea is that we wish to have a program that we have now called Mariscope. We wish to collaborate with biologists and with meteorologists, because if we put an acoustic sensor in the ocean, why not make it multidisciplinary? And with the new generation of mermaids that will last 5 years, we would hope to deploy about 300 or 400 of them globally in the oceans. But that's a project that will cost close to $30 million. So it will take some time to organize that.
Do we have other questions from the floor? Any from the chat? Okay, well, thank you very much. Thank you for your presentation, and thanks everyone for participating. We'll have our next press conference at 5 o'clock, and it's going to be about the risks of human-induced earthquakes.
Thank you very much.
Thank you.